Okay, we are going to talk about when the derivative fails to exist. So section 3.2 is about when the derivative doesn't exist. We have already looked at many places where the derivative doesn't exist, and we've discussed it. Now we're going to try and kind of formalize it and try and tell you, here's all the places where it's not going to exist. We'll also talk about differentiability in general. And yeah, so let's just get started here. There are four situations where a derivative will fail to exist. The first one is a corner. Okay, so if we just take an arbitrary graph here, so you can have a picture in your mind. A corner, probably you're not going to be surprised, is going to look something like this. Okay, so in fact all of these are, let me see, not differentiable at x equals a. Okay, so I'll just put the a on all of the places where it's not differentiable. So there's a corner where two lines meet. Here's a cusp. Cusp is another situation. There's sometimes a question of what's the difference between a cusp and a corner. What I usually tell students is, well, you can kind of tell just by looking at enough of them, but a corner is where two lines meet. Okay, so this should be, imagine this was actually a straight line here. All right, and a cusp is where two curves meet. Okay. All right, so here's A. Okay, so wherever two curves meet, you're going to get a cusp, all right? And it just won't look, well, this actually looks sort of corner-like, but, like the one on my notes here is just something like this, where it's just where two non-linear curves meet, okay? Vertical tangents, you're familiar with those probably. We call them vertical asymptotes. Oh, sorry, no, I'm sorry. We're not there yet. Okay. So vertical tangents, you'll see these in y equals the cubed root of x is a good example, where you have a tangent line that is perfectly vertical. And we looked at one of these in one of the labs, I think, but so right here, say this is A, right there. So right here we have the tangent line goes vertical for a second. It's not differentiable there because it's the derivative is the slope of the tangent line. The tangent line is straight up and down. A line that is vertical has a slope that's undefined. Okay, so vertical tangents, and then discontinuity. And this can happen in a number of different ways. I don't know if I can get them all on one graph here or not, but any type of discontinuity. So let's see. So maybe you have like a jump discontinuity, right? And then maybe you have a removable discontinuity, and then maybe you even have a vertical asymptote. Okay. At all of those places, all of those discontinuities, I'm not going to be able to use A, but A, B, and then maybe C. At all of those places, you're not going to have differentiability, okay? And that leads us to our next point, my next point, I guess, which is that differentiability implies continuity. So if you have differentiability, well, actually, two things. I'm sorry. I'm getting ahead of myself. So the first thing is, that is an important point in this lesson, is that differentiability implies local linearity. Okay, local linearity. What that means is that you can zoom in on a particular point and it will become a line. You can what I call linearize the function. Okay, so differentiability implies local linearity. And then I'm going to give you this one too. It's not quite the same order in my notes, but also differentiability implies continuity. And this is one where you want to get the direction of the if-then statement correct. All right, differentiability implies continuity. Continuity does not imply differentiability. You can have a continuous curve. It can be continuous at a point, and it is not differentiable there. Okay, again, this first one means that I can zoom in, turn it into a line. This one means that if it's differentiable at a point, then it's also continuous at that point. It has to be. Okay, so I don't think we actually need to do that. All right, so what I want to do now is give you the instructions for doing both in Desmos and in your graphing calculator, finding the numerical derivative, okay? So in your graphing calculator, let's do this. We want to find, given the function f of x equals x cubed, we want to find f prime of 2. Okay, so in your graphing calculator, we're going to use a command called nderive, and I'll show you how to find that right now, I guess. Yes, I know my batteries are low. All right, so we're going to hit math, and we're going to go over to, or down to nderive, which is right there, number 8. So write this down in your notes as well, derive. And what the way this is going to work is you're going to type in the function, whatever f of x is. You need to tell it what variable you're going to use, so you have to write comma x, and then the value that you're, or where you're trying to find where you're trying to find the derivative. Okay, so in this one we're going to find it at 2, but you might call that your a value. Okay, so for our example here, again, just so you have it in your notes, it will be nderive x cubed x 2. All right, so let me show you what that looks like in your calculator. So we'll go x cubed, and then we're going to go x, and then we'll type in 2, and we should get 12. Now, you're going to have a little bit of rounding error, because the way that this computes it computes the numerical derivative using values for h that are not 0 but very close to 0. So sometimes you'll get a little bit of a rounding error. The true derivative here, if we were to do this analytically, we would get 12. Okay, but there's a little bit of a rounding error. That's not going to happen in Desmos, I don't think, and it may not even happen in the newer calculators, I'm not sure. But anyway, you get 12 here, so we can write this for our final answer. F prime of 2 is equal to 12. Okay? All right. So let's see. Oh, I think that was it. So I think that pretty much wraps it up. Oh, I wanted to show you Desmos. I'm sorry. Okay, so let me bring up Desmos here, and I will show you how to do nderive in your calculator in Desmos. Okay, or not nderive, but what you need to do first is define f of x. So we'll write f of x is equal to x cubed. And it's really nice in Desmos because the notation matches. So you can just write f apostrophe, watch me not be able to find the apostrophe here, apostrophe of x, and sorry, we don't want at x, though we want 2. Okay, so we get 12. All right, now that's how you do that in Desmos. I'm going to show you real quick as well, and you probably already saw it there for a second, but if you want to get the graph of the derivative, you can just type in f prime of x and it will graph the derivative. All right. The other thing is, in your calculator will do this too. It is not quite as intuitive as it is in Desmos, like most things. But if you type in x cubed for your function here, then what you can also do is type in nderive, and you can type in x cubed, comma x, and then instead of putting a point, instead of telling it to compute the derivative at a point, tell it to compute it for all of x in the window. And then what it essentially does is it plots like, I don't know, 1,000 points or something, and you'll get a graph of what the derivative looks like. So there's the first function, and you can see the derivative is going to take some time because, again, it's computing all these values. So there's the derivative in the graphing calculator, okay? And so that's all there really is in 3.2. We're talking about when the derivative fails to exist, where, the big takeaway is that differentiability means that you can linearize the function, and that differentiability implies continuity. And the last thing is, I'm not sure why I didn't write it in my notes, but when we say a function is differentiable, we mean it's differentiable at every point in the domain, okay? So like 1 over x would be a differentiable function despite the fact that there's a vertical asymptote at 0. 0 is not in the domain. Therefore, it's a differentiable function. Any function that is differentiable in the domain, we call it a differentiable function, very similar to the definition for a continuous function, right? And that's it for section 2.